Okay, for this video, I'll be going through EMI tutorial. Okay, so question 1, a wire ABC connected to a center zero galvanometer. Basically, the galvanometer checks for any flow of current. Okay, so if the galvanometer, which is center zero, and if it has current flowing from left to right, the galvanometer will be deflected to the right, okay, vice versa. So it's placed between the poles of two magnets, so these are the external magnets. Now when the wire is moving downwards, so this is the direction of the force, applied force, right? The galvanometer deflects to the right as shown. Okay, so basically they want us to find out the direction of the induced current. Okay, so for this we'll need to use our right hand Fleming's right hand rule. Okay, Fleming's right hand rule. Okay, where the thumb represents the force. Okay, first finger represents the direction of the external magnetic field. So the external magnetic field is always from north to south. Okay, so and then the middle finger will represent the direction of the current. Okay, so in this case they give us the force and they also give us the direction of the external magnetic field. Then if you apply your Fleming right hand rule, you'll find that the current actually flows from C to A. Please try. Now, is there any force which opposes the motion of the wire? If yes, there is origin. Okay, there's actually a force that opposes the motion of the wire. Okay, because the induced EMF that is produced by the downward force on the wire, which is cutting the magnetic field, okay, and by Faraday's law it will induce an EMF. So therefore we have an induced EMF, and because it is a closed circuit, okay, closed circuit, so therefore there will actually be a current flowing. Okay, now how will the current be flowing? We predicted the direction of the current flow using Fleming right hand rule. Okay, but actually that doesn't explain why the current flows that way. Okay, Fleming right hand rule only tells us the direction of the current is like that, but he cannot explain. Okay, the one that can explain the direction of the current flow is Lenz's law. Okay, so if let's say we apply right hand grip rule, to the direction of the current here. Okay, so I will have, let me use another color. I would have for this direction of the current, right, I would have using my right hand, which represents direction of current, I will have at the top the blue color is the magnetic field due to the current flowing, but because it's circular, okay, so I only focus on the top and the bottom. At the bottom it's actually this way. Okay, so you find that actually at the top the magnetic field cancels out each other. At the bottom, because the magnetic field of the external is also like that, same direction, so they actually reinforce one another. Okay, so the magnetic force is from more magnetic field to less magnetic field, so therefore the force is upwards, which then opposes the direction of the applied force. Okay, so this is what it means over here. The magnetic field produced by the induced current, so we have to use the right hand grip rule to determine the direction. So if I'm looking at it from this side, my eye is looking at it this way, I would see that the current is in this direction, right, coming out of the page. I have my north, I have my south here. So this is the direction of the external magnetic field, and this is the direction of the, if I apply Fleming, if I apply right hand grip rule, okay, on the top it will cancel, at the bottom it will reinforce. Okay, I think I talk about this a lot in class, right? Therefore there will be an upward force. Okay, to which side will the galvanometer needle deflect if the wire is moving upwards? Okay, so reverse direction, so it will be to the left because the direction of the induced current will be opposite. Moving in the positive x direction, so this is the x direction, positive. Whether positive or negative, there's no deflection, okay? Because this is, let's say, the external magnetic field. If I move my wire all the way like that, parallel to the x-axis, there is no cutting, there's no change in magnetic field strength by the conductor, okay? So according to Faraday's law, there will be no induced EMF. Moving in a positive y direction into the paper. So again, this is the external magnetic field. So now if I get the wire to shift in and out or into the paper lah, okay? So actually again, there's no cutting. So again, there's no deflection. So it must really cut. So what happens just now when there is an induced current, right, is when my wire is going in downwards. So it cuts here, there's no cut, cut here, no cut again, cuts again, right? So there is always a rate of change of magnetic flux. Therefore, then there will be induced EMF. But for part 1 and part 2, there's no change. Now explain how and why will the induced current change, if any, if the separation between the two magnets is reduced. The magnetic field strength between the two magnets will become stronger, right? Because I bring the two magnets closer together, then this will lead to a greater change in magnetic flux linking the wire. Okay, learn how to write like that. Okay, and this is the basis for the Faraday's law. So you cut the field lines, therefore a larger induced EMF, and therefore a larger induced current. Okay, so this is the template to explain. What happens if the wire is moved downwards faster? So there's a larger rate of change of magnetic flux, therefore larger induced EMF, and hence larger induced current if it's a closed circuit. Now the wire ABC is folded and moved downwards as shown. Okay, so if it's moved downward as shown, the force on this side is down, the force on this side is down. Okay, so just now we see that the current will flow this way and the current will flow this way, right? So the current both flows down and they are in opposite directions, so they will cancel each other. Okay. Okay, question 2, we see that there are actually two coils. So what happens to the bulb at the instance when the key K is closed? When it's closed, there will be current flowing, right? So if current flow, it will produce. So number 1 is current flow. Number 2 is produce magnetic field, right? Because whenever current flow, you'll produce a magnetic field. Okay, then we can apply our right hand grip rule for solenoid. And if you have drawn all these little arrows to show the direction of the current, right, then you apply your right hand grip rule where the fingers represent the direction of current. So here will be a south, here will be north. Okay, so suddenly this coil here on the other side actually experience a change in magnetic field. How so? Before the switch is closed, there is no current flow, no magnetic field. Now that the current is flowing, there is a magnetic field, right? So from no magnetic field to having magnetic field. So then there will be induced EMF. So why will what is the direction of the current flow, the induced current flow? Because this is a south, so it must oppose it according to Lenz's law, right? So over here will also be a south, right? So if south, then here is north, then you apply your right hand grip rule for solenoid again, you'll find that the induced current, this is the induced current, will actually flow in this direction. Okay, but let's look at the question. Explain what happens to a bulb. The bulb will light up momentarily. Why is it only momentarily? Because when K is closed, there's a magnetic field produced, right? Results in a change in magnetic flux linking the right solenoid. And by Faraday's law, it will induce an EMF and hence an induced current. But why momentarily? Because after that, there's no more change. The current continues to flow. The magnetic field is continuously south and north, okay, with no change in magnitude. Therefore, there will be no longer a change in magnetic flux linking the right coil. Okay, So if the key K remains closed, bulb remains unlit. It will be off. As K remains closed, magnetic field produced by left solenoid remains constant. So there's no change in the magnetic flux linking to the right solenoid. Therefore, by Faraday's law, no EMF is induced. So when we open key K again, so just now remember when K is closed, there is a magnetic field produced. But now when key K is open, there is no more magnetic field. So again, the right solenoid experiences a change in magnetic flux. Okay, from having magnetic field to no magnetic field. So again, by Faraday's law. Okay, what would you observe if K is closed and open at a frequency of 2 Hz? So the bulb will flash flicker at a frequency of 4 Hz. 2 cycles of close and open. Now, suggest 2 ways to increase the brightness of the light bulb. This one you should know, more turns. I think a lot of you are also writing more coils, which is wrong. Okay, please write this down. More coils is not correct. You need more turns. Okay, so it can either be more turns in the coil on the left or on the right. A stronger battery so that I have a larger current. Larger current means I have a larger magnetic field produced. So later on, when you on or off, there will be a larger rate of change of magnetic field. Or use a soft iron core, because if you notice, it is actually a paper cylinder. So the iron core will actually concentrate the magnetic field lines. Okay, question 3 looks similar. P and Q are 2 coils of insulated wire. Coil P is being connected to a 36 watt 12 volt battery. So this is my P and V. It's observed that the lamps will light when an alternating current. So the current changes direction, which means the direction of the magnetic field produced will also keep changing. Therefore, the lamp, the solenoid that's linked to the lamp will experience a change in magnetic field. Okay. So account for the observations described. With an AC, the current changes direction periodically. This produces a constantly or continuously changing magnetic field around coil Q. So according to Faraday's law, it will induce an EMF. But with DC, the magnetic field produced will remain constant. No change in magnitude and no change in direction. So therefore, there's no change in the magnetic flux linking the coil. Okay, so we see the same kind of answering template. Now with the alternating current supply, connected to Q, why will the brightness of the lamp decrease if P is moved away? If it's further away from Q, right, the weaker the magnetic field due to Q. This decreases the rate of change, right? So by Faraday's law, the induced EMF is smaller. So basically, there are 3 persons here. Faraday, which is the rate of change of magnetic field. So it will lead to EMF, induced EMF. Okay, then for lenses, it will be to explain the direction of the induced current, and for Fleming is to predict the direction of the induced current. Okay, so you need to know the role of individual. Okay, so if Faraday is always talking about the rate of change of magnetic field to induce an EMF. Okay, then part C, with the alternating supply connected to Q, an aluminum rod held along the axis through the center of P and Q becomes warm. Okay, but a plastic rod does not. Suggest a reason for this. So if you know, aluminum is a conductor, but plastic is not. Okay, so when the aluminum rod is used, the change in magnetic flux linking the aluminum rod induces an EMF and current, since it's an electrical conductor. So it causes the rod to heat up. But on the other hand, because plastic is not an electrical conductor. Okay, then a man makes an anemometer, a device for measuring wind speed, of the apparatus shown. So you see there's a magnet, and this magnet actually turns, and therefore this coil of wire will actually experience a rate of change of magnetic flux if the wind causes the magnet to turn. So this is always the narrative of this chapter. Okay, so describe how the anemometer works. The wind applies a force causing it to turn. This causes the magnet to turn and the magnetic flux linking the coil of the wire to change. Therefore, by Faraday's law, induces an EMF in the coil. Okay. Okay, next part. Now, when the wind speed varies, the speed at which the magnet rotates also vary, right? So it affects the rate of change. So it's not just a change of magnetic flux, it's also about the rate of change. Okay, and therefore the EMF induced will change with the wind speed. So it can be measured by the voltmeter. Now, how do we improve the sensitivity of the anemometer? So increase the surface area of the rubber cups, right? More rubber cups, larger surface area, you can capture more wind, right? Add more cups. Increase the number of turns of the coil, right? So again, turns of the coil, not the coil. Use a stronger magnet and use a more sensitive voltmeter. Okay, figure 5.1 shows an ideal transformer. So now we are going into transformer, and because it is ideal, right? It has 200 turns in the primary. So I will put NP equals to 200 and NS as 400. Okay, for O level, the primary is always on the left hand side. Okay, that makes secondary on the right hand side. Now, a short-lived current will be induced in the secondary coil at the instance the switch is closed. You notice that this is our DC, right? So we have direction of current flowing. So the current direction is shown by the red wire. If you apply your right-hand grip rule for solenoid, okay, you'll find that this is a north, right? So by Lenz's law, there will be a north here, right? To oppose the direction of the induced current is such as to oppose the change producing it. To oppose, since here is a north, then it will be a north here. Okay, then again you apply right hand grip rule for solenoid and you'll be able to find the direction of the induced current. Okay, so I explain why transformer can be used only with AC supply. So I think previous questions we have done this. AC supplies a changing current, changing magnetic field, therefore there is a continuous change in magnetic flux linking the secondary coil, then by Faraday's law. Okay, so now the primary coil is connected to a 10 volts, so our VP equals to 10 volts. Okay, so what is the voltage across the secondary coil? We have to use the turns ratio formula. Okay, the more the turns, the more will be the voltage. So they have this formula. Doesn't matter MP over NS, it will be equals to VP over VS. Okay, so more turns, that means more voltage. Where do we see this? Over here, right? Increase the number of turns, right? So that you have larger induced voltage. Okay, so if we were to sub in, we'll get 20 volts. Okay, because the number of turns of the secondary compared to primary is 2 times. Therefore, the voltage will also be 2 times. But this is only if the transformer is ideal. Now, what's the frequency of the current in the secondary coil? So they should have the same period. So if we look at the primary, we know that one complete cycle is 0.05. Alright, so I will get 20 hertz because 0.05 is the period. Now, the galvanometer is replaced by a resistance of 100 ohm. What is the current in the secondary coil? So you can use our Vs over R. We'll get 0.20 ampere. Now, calculate the current. Okay, so because we start off with PP equals to PS, that means ideally, the power in the primary must be equals to the power in the secondary. Cannot be more, right? It can be less. If it's less, that means it's non-ideal. Okay, but cannot be more. So PP is IP VP equals to ISVS. Okay, so we can actually have this relationship. Remember, NP over NS is equals to VP over VS. And if I were to make VP over VS in this formula, okay, VP over VS, I will then get IS over IP. So this is the formula that I can come up with. okay, that links MP, VP, and IS if it is a ideal transformer. So with this, I can get 0.40 ampere. Okay, explain why in practice the efficiency is always less than 100%. So this one maybe you need to memorize. And suggest 2 ways to improve the efficiency. Use low resistance wire, okay, or use a laminated core. Resistance wire, their resistance, don't forget it is rho L over A. Okay, so I can use a low resistivity material, or I can increase the surface cross-sectional area. Okay, a transformer has 20,000 turns on the primary coil, so this is my MP, and 400 turns on the secondary coil. That means this is actually a step down, right? So efficiency is 100%. Determine the output when the input is an alternating supply of 240. So this is my VP. Okay. So with all this information, I use my turns ratio formula. I should get 4.8 volts at the same frequency. Now, transformer is used to operate a 9.6 W watt lamp from the 240 volt supply. Calculate the current. Okay, so the power is 9.6 watt. Okay, so this is from the 240 volt supply, but we cannot be using this because it's from the supply. So how it will look like is this. This is the primary coil. This is secondary. So primary I have more. Primary I have more. Secondary I have less, right? So over here is actually 240 volts. Okay, and when it comes to here, it becomes 4.8 volts. I have the lamp that is connected. Okay, so this is the voltage. The power is 9.6. Therefore, the current is 2 ampere. Now, what's the current in the primary coil? Remember, we have this formula VP over VS equals to IS over IP, right? So I can substitute my IS as 2. My IP is unknown. I have VP and VS, so I should get 0.040 ampere. You can check your working. Okay, question 7. A remote village is supplied with electricity from a power station some distance away. So whenever you see this, you'll come into my P equals I square R. Later we'll be using, as well as the transformer. At the village, the transformer steps down the potential difference from 10,000 volts. So this is my VP. 250 volt is my VS. Okay. So explain why a high voltage of 10,000 volts is used to transmit the electrical power. Like what I said, when transmitting at a high voltage, the current will be low. Okay, so having low current reduces power loss because power loss is given by this formula. Okay, so the form of energy transferred by heating to the internal store of the cable will be very little. So power cables are usually quite thick. Explain the reason for doing so. Okay, because R equals to rho L over A. Okay, with a thicker cross-sectional area, the resistance will be lower. Okay, so because the law of energy will be transferred by heating to the internal store, right? So to prevent overheating, I should have them having as low a resistance as possible. Now calculate the current flowing in the secondary coil. Hence calculate the current in the primary coil, assuming that the transformer is 100%. Okay, so what were we given? So the 500,000 is the main power supply. So this one shouldn't be mean. The main power supply to the village is 500 kilowatts, which means this is the PP and also equals to PS. Okay, so we know the IS. Did we calculate IS? No, not yet, because we only have VS. So we can actually find what is IS. Okay, IS, yeah. Then again, we apply this formula. We can get IP to be 50 ampere. Please try it out. Okay, if the power cable have a resistance of 20 ohm, calculate the power wasted in the or transferred to the cable. Hence, deduce the power the cable must draw from the power station if the village is to receive 500 kilowatts. So basically, we use power loss is P equals I square R. The resistance, we take it that is 20 ohm, so it will be 50,000. Okay, so in order to cater to this, we need an additional of this 50,000. That's why it will be 500 kilowatt plus 50 kilowatt. Okay. Okay, question A, it shows a Christmas lighting set containing 60 miniature bulbs, each of which is rated at 2 watts, 5 volts. Okay, so it will deliver 2 watts of power if the voltage across it is 5 volts. Okay, and they are all connected in parallel. So this is the mains of 220 volts. So this is my VP, and my VS is 5 volts, right? Because this is a transformer. To operate the lighting set normally, it's found that a transformer is needed. Calculate the turns ratio. So turns ratio, it can be, it is NS over MP. Okay, NS over MP. So NS over MP, that means it is VS over VP. Okay, because it's stepped down, therefore my VS is 5, lower than my VP of 220. So I'll get 0.0227. A lot of you will be tempted, important, to leave your answer in fraction. No, you have to convert it to 3SF. Okay, so even if it's a ratio, it should be to 3SF. Now, assuming that the wires have negligible resistance, calculate the equivalent resistance of all 60 bulbs. So we can use the P equals to V squared over R formula to find R. So basically, we have learned these 3 formulas. Okay. So P equals I squared R, as now you now you know, it is purely for the power loss in the transmitting cable, right? But if you know your I, you know your R, you can go on to calculate P in any case. But this is the general one to calculate power. If I have current, I know the voltage, I can calculate the power. Then this one is if you are given P and V, then you can find the resistance of the light bulb. So this is what is happening here. Okay, and because they are all connected in parallel, right? So you can actually take 12.5 divided by 60. Okay, yep. So calculate the current in the primary coil. State your assumption. We have to assume it's 100%. So the current, we use P equals IV. The V is 220. Now the power is 2 times 60. Where do we get 2 times 60? Because each light bulb is 2 watts, so I have 60 light bulbs, so I should have 120 watts. Okay, so yeah. So this is the end. Thank you very much.